Good afternoon, everyone. Good afternoon. My name's Kevin McLaughlin. I'm the Dean of the Faculty. Welcome to all of you to the next installment of Thinking Out Loud, the Presidential Colloquium Series. As Dean of the Faculty at Brown, I'm very pleased officially to welcome Dean Arlie O. Peters to Brown. Let me take the liberty of noting that, very briefly, that as I read through the materials sent to me about Dean Peters, the word spectrum came to mind. The remarkable spectrum of his work and his academic appointments, from the applied to the pure, from business administration at the Fuqua School of Business at Duke to the Department of Math at Princeton, from academic administrator to faculty member and engaged intellectual. And finally, I think in anticipation of his talk today, a sort of spectrum within a spectrum, from the illuminated portion of the universe to what he calls cosmic shadows. So with that very brief welcome and introduction, I want to turn the mic over to Chris Rose and thank him for organizing this series. And thank you, Dean Peters, for coming, and I welcome you to ISERM and to Brown.
Okay, Kevin, thank you so very much. Kevin is he's an English professor, and somehow you always pull things together in such a silver-tongued fashion that I hate going after you. All you need is the text. In any case, this is Thinking Out Loud. How many folks, I always ask this question, so how many recidivists do we have here? How many, so we're down in only a few. This is great. All right, so we have a new crowd. This series was put together to showcase a special sort of talent. So, I could go into all of Arlie's, stuff, and basically everybody has a program, right? So it's on these seats, so I hope you grab a program. If you want to know about Arlie's particulars, just pick that up and read it, because we're not going to do that now. But I want to do a quick couple of things. First thing is to thank Chris Paxson. This is funded and supported by the President's Office, so they've done a wonderful job. This is our 5th year. Arlie is our 15th speaker. And the other thing that I want to do, this is the first time in this particular venue. So thank you so much, Brendan. This is ISERM. This is absolutely beautiful and fantastic. So what is this series about? What we do is we're bringing in people that, the way I like to, they're a little crazy. That's the only way to put it. They're a little crazy. They think about the world in different ways. And that's what you want when you're trying to do science, and especially science in the 21st century. So Arlie is one of those. The funny thing is that you are the 15th speaker, but at the risk of insulting all of our other speakers, one of whom we hired, Jim Gates, you kind of embody what this series is about. So he's a mathematician and a physicist. Yeah, what big deal. There's lots of mathematicians and physicists. But he also, he's thought broadly for as long as I've known him. And that's something that is really precious and wonderful. And one other small little, factoid that I'll tell you about Arlie. So we were puppies together. So I was the big old, I'm about 6 years ahead of him. So I'd gotten my Ph.D. We were funded by the same program at Bell Laboratories back in the day. And we were trained at the same graduate institution. So there was some gathering where, the really, experienced folks like me, 6 years older, were advising these youngsters. And Arlie said something about, yeah, I'm doing string theory and whatever else. And I said, well, that's really great, but, you basically, make sure you have a day job. But here's the thing. Arlie, even at that tender young age, he looked up at me and said, no, this is why string theory is important. It relates to this, and this. And I walked away like, oh, God. This guy is really brilliant. So I guess with that's really, I've embarrassed you enough, right? But you are exactly what this series is about, and I'm really looking forward to this talk. So thank you, Arlie. Thank you. And you're all mic'd up.
And you get a handshake too.
Sure. Great. Of course. So Chris, thank you for that warm introduction. Kevin, I appreciate it. Brandon, the hospitality. So first you'll notice I don't like standing at a podium. I get restless. So I'll hover around, and the way I like to think about it is I want to tell you stories. And these are stories that come from an intellectual travel. I will do my very best to make it accessible, but at times, I don't know if this has happened to you, but you hear an accent from me. You know, you go out for dinner, you sit around a table, and then two people from their home country start talking in their own language, and you have no idea what they're talking about. So from time to time, I will be slightly rude to make sure I talk to some of my colleagues in mathematics, some in physics, just to let them see some of the underlying structures and connections in these stories. But I promise they will not last longer than a minute. Yeah? So bear with me. You may tune out, but tune back in. So the story begins with one of my heroes, and that is this man. Einstein wrote an essay that is particularly profound for a field, but you know the big breakthrough for him was in 1915, in which he predicted how much starlight would be bent by the sun. So imagine here's the sun, and then you have a ray of light come, and you discover light doesn't travel on a linear path. Gravity is going to bend it, and it does something like this. It's this angle, that bending angle, that Einstein calculated in his theory, in his gravity, and when you compare that to the Newtonian value, Einstein amount was like twice. And so he had a testable prediction that would allow you to see the difference between his theory and that of Newton. Now, this entire journey is going to be one that deals with the interplay of light and gravity. So there's an essay that Einstein wrote. It's just a page and a half long. This was in 1936, and I would encourage you to take a look at it. In that essay, he made two interesting observations about light and how gravity would act on it. And we try and represent it here in this picture. So in this one, oops. So I will get, yeah, here we are. In this picture, this technology is very fancy. Wow. So where's my IT guy? I just want to take you back to this picture from Einstein. One more. Here we go.
I can do the Vanna White thing if you want.
Good, good. So let's take a look at this. Here you're on Earth looking through your Hubble Space Telescope. Here's some deflector of light. It could be a star, it could be a galaxy, or something of this sort. And then over here, I promise you I'm going to get used to this. And here we go. Okay, I'll be very careful, or else I'm going to start using my own laser pointer. So here is a star you could think of, a source of light. And what Einstein pointed out in the essay is that if the source of light is off the line of sight for your telescope, you're going to see two images of it. And in the next picture, you'll notice the source of light is on the line of sight. And he concluded that if it's on the line of sight, it will appear as this formally infinitely bright ring. So the first thing you should take away from this is there's a difference in the background if you're off the line of sight or if you're on it. So it's interesting. He was reluctant to publish this essay. It was the engineer Mandel that urged him to do it. And say, okay, I'm going to ruin my reputation a little bit, and I'm going to still publish it. And in there, he indicated his skepticism that this would ever be observed. The fact that that gave birth to the field, by the way. The fact that I'm standing here, so let me do this gently, one tap. That means that there's something interesting going on. So if you take Einstein's 1936 essay, we are going to take it and reinterpret it with more modern technology, more modern intellectual technology. And so a simple cartoon for you to keep in mind is this. Imagine here you are on Earth looking out into the universe, and then here on this plane is where your lens would be, and then in this background plane would be where your sources of light will be. And so, like before the light travels to you, the gravity of this matter distribution deflects it by that angle alpha. Now, the two assumptions you make in this model is that the deflector is thin, and that's a reasonable assumption, actually, which is why we put it on this plane. This assumption here is because the distance from here to there, the distance from here to there, it would be like 1,000 times the diameter of the lens. So that's why we do this when we're conducting the modeling process. The other assumption we make is that the bending angle is not very big, and it's typically arc seconds that you're going to be looking at. If you saw Einstein's prediction, 1.74 arc seconds. That's pretty tiny. So you're not going to look like a 30 degrees, 180 degrees type deflection. That happens when black holes deflect light. You wouldn't believe with these two basic assumptions, you can build a whole mathematical theory. And so let me show you how that happens. Not bad, I'm getting used to it. So what mathematical physicists do is they take a physical system, they build a simple picture of it, but to make predictions, you need equations to come out of this thing. And it turns out the light will give you the formulas that you need. So in this picture, it turns out there's a theorem that tells you could reverse the light rays without changing the physics. And now I'm going to speak in the language of the mathematicians. This is simply talking about linear reparametrization of null geodesics. That's all that happens. But in a physical sense, none of the physics changes, which is really cool. If you do that, look at what happens. It means that you're shooting cannonballs, right? Here's a light ray, deflected by the gravity, there's a lens here, and then it goes by that angle, hits here at X, and then goes to Y. You'd have another light ray go, it'll hit here, bend somewhere, and then they start piling up on that background plane. What I just did was to describe to you that the light induces a transformation from L, the lens plane, to S, the light source plane. And so for mathematicians, you get something that we would write like that. And then this transformation, I gave it the name eta. So eta takes the point X and sends it over to Y, depending on how gravity bends the light. Now, one more slide I'll show you, and then I'll get away from the equations and return to some beautiful pictures. Using cosmology and all that great stuff, you're solving the Einstein equation, you can actually find a formula for this left-hand side. And I won't give you much details, but it looks something like this. It has a name, we call it the lensing map. This is the structure of the formula, and this alpha relates to that same bending angle we were talking about. So if you ask me in this equation, where's the distance between the lens and the source, where's all your cosmology, I claim everything sits right here. Here's a more detailed expression for it. So we could return back to the more general picture of what's going on by applying this idea to Einstein's essay. No, Einstein didn't do it like this, by the way. That's why I said we're using more modern technology to rederive the results in his essay. So if you use the same geometric picture, we retrace the light rays back using that equation I told you, and you'll find out that it's going to hit the plane at 2 points. So there'll be two solutions to that equation, and then they'll converge at this point. Those are the double images. One other detail I'll mention, notice I made one dot bigger than the other. It's because one of the images will be brighter than the other. Remember, Einstein was skeptical that this would be observed? Here we go. That's a double image of a distant quasar undergoing gravitational lensing. Let us do the ring. Similar thing, you trace the light rays back. There's now, with the new technology, this ring, we call it a critical curve in general, but in honor of Einstein, it's called an Einstein ring. And then this piece where the light rays will converge right at that point, that's a very bright spot in the background. I'm already hinting there could be shadows, bright and dark areas. So that thing we call a caustic. Remember, caustic means burning bright. And look at this. Here's an Einstein ring. This is white ring right here. This piece in the middle is the lens. So these things were actually observed.
So Arlie, what is the, there's matter
that's
creating
right.
gravity. So what does it look, so the lens is just a distribution of gravity, of mass. So
That's
what
right.
does it look like?
It's an actual galaxy.
So it's
In
just
this
a
case, yes, it's one galaxy. It was also a galaxy. So I'm showing you examples of galaxy lensing, right? So at least I think I've convinced you so far that Einstein perhaps was a little too skeptical. Now, let us extend the story some more. That's the first little story I wanted to share with you. Here are many other examples of either full rings or partial. These are from the Hubble Space Telescope. The partial rings occur when the source might be slightly off and extended. We have found, I say, complete rings close to half a dozen. Partial rings, I mean, probably 30 or 40 of them. The double images, oh my goodness, they're in the hundreds now. So this field has become one of the very active areas in astrophysics. One other picture I want to show you is, well, you say, wait a minute, Arlie. You have the thing deflected once, but if you're going to cut across the whole universe, you may get deflected many times. And I say, yes, of course. The same thing I described to you, that model, you could extend it to many planes, except here in the representation, the critical curves will be represented in the first plane, then the caustics become curves, more complicated in the back. That is the basic, I would say, cartoon picture of what's going on. So let's go a little deeper. If I pick, let me just refresh your memory with the previous one. If I pick a little patch around one of these critical curves, there is a result that tells you one of two things will happen. So this is a little patch in the lens plane. The way you could picture it is, imagine you have this little piece and you fold it like that and squish it down so the whole thing goes over on this side. And the caustic now is not a point, it's partly a curve. This is just in a little area. What this theorem tells you is that if you're a source of light and you sit here, there are going to be two images of this locally that are near each other. And the other possibility is this little patch, you pleat it, like a little with cloth, yeah? And you squish it down, and then the caustic has this point. If you sit inside here, there'll be three images locally. There could be other images elsewhere. This is actually a theorem from differential topology. This is the Whitney singularity theorem, right, for the pure mathematicians here. Let me show you this with the cosmos. So let's get away from the abstraction. When a galaxy that's transparent acts as a lens, this is what the caustics in the background look like. You get like a diamond shape, and then you have this more oval shape. What I'm saying is that's where most of the light rays will pile up. And then the critical curves, which are on the lens plane, will take this geometry. Here, there's a tiny one there. Notice now when the source sits at that point, there's the doublet, and then the other images that you may get, right? So the prediction of the theorem actually was observed. Isn't that amazing? Right? This is the scientific method, right? Now I'm skipping all the mathematics and all the analysis, but at least I'm convincing you that this model is making predictions that are testable. Let me show you. Yes, we have many. In fact, if you want to have fun, you should go to the Hubble site and just search under gravitational lenses. You'll see many examples. So let's do the other part of the theorem that showed the triplet. So here, remember you have to, this square is a little too big. You're sitting right inside that cusp. This is a triplet that Whitney's theorem predicts, that theorem in pure math. And then look at observations. Isn't that awesome? 4 images of a background quasar being lensed by a foreground galaxy. I remember the first time I saw these things, I said, wow, that is science at work, okay?
So how do you determine that it's multiple images of the same?
The spectra,
Spectrum.
the same redshift. So we have a list of criteria that you use observationally. And you will get the same at any wavelength. Right. It's an image of a background quasar, and the lens is a galaxy that's causing it, the gravity. Yes. Okay, so let's continue this. So this has to do with multiple images, right? Now, let us go on, and I'm just refreshing your memory. Remember, the caustics live here, and then the multiple images we project over here. Well, I just want to give you a little terminology. So I'm going to take you on a tour now into the cosmic shadows. I showed you a little about multiple images, and I sort of just tangentially spoke about these things called caustics. So when I say magnification pattern, I mean the full arrangement of shadows and illuminations. It's the same sort of thing when you drive to work, you look on the ground, you're going to see all kinds of patterns. Gravity acting on light, deflecting the light, focusing in some areas, spreading it apart in others, creates shadow patterns in the universe. Right? So I'll give you examples. If you have a star as the lens, and that star is embedded in a galaxy, the galaxy is going to act on it in a certain direction. The galaxy is the gravity from outside. And that's simply what we're referring to as shear. This is what the shadow pattern looks like in the background for a star with shear. It's a beautiful asteroid shape. And notice 4 cusps. The way you think about it in this representation, the green is the darker areas. This is the next step up from green, then red going brighter, yellow is brighter, and then white would be the brightest. Notice each cusp has a lobe of high magnification around it. So what this means is that if you cut across this caustic, I could barely see you because you're in the shadow, you go, go, go. You hit this, suddenly I see you, because you get bright. And then as you move away from the yellow, your brightness drops, goes to a minimum, comes back up, cuts here, and then you're super bright again. And as you cut back out, you drop into the shadow region. That's one way you could think about it.
So what length scales are being applied as you go across the continent?
So you want to hold that thought until I get to finding extrasolar planets? Okay, good. See, we here, everyday life. You notice how you have the cusp and the lobe of high magnification. This one I actually took at home. I had a glass of water, and I had the light on, and I noticed, I said, I need to take this picture and bring it in. Notice that, like in the cosmic case, let me just show you this other one to refresh your memory. I don't want you to forget this. Notice how this side is dark, and then you have this bright band along there. You also have that, right? There's the bright band. So you could see this inside your coffee cup as well. If you have it hot enough with some cream and at the right angle in the light, you're going to see this caustic pattern. Okay. Let's get back to the universe. This one, if you have a star, and then you hear people talk about dark matter, continuous matter, if it's sufficiently dense, you would get something that looks like this. There's a big shadow here. This now is the caustic, so outside is brighter than in there. And in fact, it could get so dense that you will become invisible if you sit inside here, and you would be invisible at any wavelength. And that's why we call it a blind spot. You know, the eye has a blind spot. There are blind spots in the cosmos too. Which is great, right? Because where do we now have our intergalactic war? We must place our spaceships in blind spots, right? The enemy won't be able to detect you. Let's continue. This one is due to several stars. Notice how they get more and more intricate. This, I'm from Belize, we're on the coast. I'm sure many of you have seen this before. There they are on the side of a boat, and they jiggle around, right? Because the water is the lens, and it's causing that kind of activity. Notice you can have them overlapping in interesting ways. Here's a dark region. It's just, to me, a very beautiful set of geometric patterns. This one is a section due to like 100,000 stars. If you take the stars and you add planets to them, look at this. This like just blew me away the first time I saw it, right? It looks like a neural network in the brain.
Is this a simulation?
Yes, and then we'll show you how you get the observations out of it. Right, it's really remarkable. And I'm just showing you examples. So if you want a challenge for the mathematicians, I hear that 5 stars are put on a regular polygon. It's a beautiful geometric shape. You should count how many cusps there are. So you have, let me just show you this quickly. Notice each triangle, oh boy. Okay, so each triangle will give you 3, and, okay, I'm almost there. Here we are. So if you should try, I always do this with kids. Here is this, and that is that. So they're 32. It's really beautiful the way they wrap over each other. And so the more symmetry you put in the lens, the more intriguing a set of geometric caustics you get. So I did this because that 32 is not an accident. The theorem that I had done early on says that you will get an even number of cusps, even if you have multiple planes acting as deflectors. That is interesting, right? So you can't just have an odd number in total. Okay, continue. Another thing that happens is if you hike up the continuous matter sufficiently, here is how the pattern would look at the beginning. As you hike it up, notice how it evolves evolves, and eventually you get these oval shapes with no cusps. So you have a cusp illumination theorem. I don't know yet how to prove this for K-lens planes, but we could at least prove it for one. Okay, so I'm giving you a flavor of some of the general results. This other one, I want to take you inside this a little bit, because you can't come to a thinking out loud talk and walk away not knowing how to do a little bit of math, right? So let us do this geometric kind of math together. So what I want to do is to calculate the curvature of these caustic curves. And what you're going to do, I'm going to orient it, meaning I'll give it a direction. So don't pay attention to anything else up here. Just look at this asteroid. I'm going to walk along it in such a way that to my left, I will have two more images than to my right. And that's what happens here. Okay? That's the direction I'm doing it. And then over here, when I put a tilde, I'm just rounding off, making it a nice, smooth curve. So I'm rounding off the sharp edges. So there's a formula for you to calculate the curvature of the fold arcs of these caustics. Just think of the curvature, the bending, total bending of the caustics. Here it is. It looks something. This is 2 pi, and then this number is the rotation number of that. So you'll have to do it how many times you end up going clockwise, counterclockwise, clockwise, this kind of thing, because it has a direction. And then here, this is just the number of cusps. Well, like here, it's 4 cusps. So this is the one, how you calculate that, I want to show you. So that's just a little bit of math I hope you could take away. So just focus on this. Ignore that. Here's your caustic. It's this triangular shaped thing. There are 3 cusps. So I put the formula here. You plug 3 there. That's where it came from. Now we need to figure this part out. So you have this nice smooth curve, and I want to get its rotation number. So here we go. Imagine I have a little stick and I walk along. Here it goes, it goes, it goes. I follow it, come around, come around. I just made 1 counterclockwise move. And that's +1. And that's where that comes from. Clockwise, that is going to be -1. And you do the same thing here. 4 cusps, that's where the 4 comes from. The shape didn't matter here. It's a simple closed curve. And so you get a 1. And so you can imagine just calculating these things out. And for fun, we did a more complicated one. And here you could count the cusp. It's 8. But then there are 1, 2, 3, 4 little counterclockwise loop, and 1 clockwise 1. And so that is 4 minus 1, and that's where I get the 3 from. Okay? There's a theorem that says if the light could pass right through the lens, this number will always add to 0. That's what I mean by a smooth lens. But if the lens has G stars, then this is the formula for the curvature. All right? Well, let us do a couple of examples. I'll just do this quickly for you. Just this left one, remember you saw this before when we were looking at the doublet and the triplet. We already calculated this curvature, and that's here. For this one, it's simply a counterclockwise curve, and the formula gives you this, adds up, you get 0. The theorem is correct. You do a similar thing here. We already calculated that. We did this one already, did that. Plug in the values from earlier, you get -4. Checking it against the theorem. G is 2, so 2 times 2 is 4, and that's how you get -4 pi. Nice, beautiful, happy. Well, let's not be happy for too long until I encountered this. So I was very proud of this paper. This is the simplest caustic you could imagine, right? It's simple. It looks like a circle, except it's clockwise, so that will give you a negative in there, right? Nothing else. So what does this tell you? It's going to give you a curvature of minus 2 pi. This is a caustic due to 2 stars, so the G is 2. There is a problem. Because if you plug 2 here, you get minus 4 pi, and the thing is telling you it's minus 2 pi. When I saw this, I said, oh my goodness, the paper is wrong. I felt like publicly embarrassed. And when I was settled down enough, I checked the proof. I couldn't find anything wrong with that proof. And so I asked my friend Hans Witt, who did the simulation, to check the code. Hans looked carefully. He couldn't find anything wrong with the code. I had a predicament. They both can't be correct. There's a contradiction. So I don't know if there's something subtle in the paper that I couldn't find. I had other people look at it. The proof was correct. Hans' code was correct. And look at what happens. Hans figured this out. He, for some reason, said, I'm going to zoom in on this part of that caustic. And look what happened. There was a missing caustic. It was this little fellow right here, the exotic caustic. And when you now recalculate, you get the minus 4 pi, and all is well. This is part of the research experience, right? Remember, we're exploring and digging into the unknown, and there will be times when you think you have a discovery, and you think it's wrong, and you just go through this confused state, right? So I don't want to ever give you the impression that it's a nice, smooth journey, and you just get beautiful results, and it goes on and on. So everything I've done so far, it's more in the theoretical realm. You notice that there are theorems in mathematics that are coming out. We're able to take Einstein's essay and do it in a more modern form. And so this is really, I would say, an engagement in a bit of pure mathematics. But what this has to do with physics, and why is this important? So I want to just leave this with you before I go to looking at extrasolar planets. On the left is an image, I'm from Belize, the beautiful islands, of water off one of the keys. And on the right is a large-scale structure of the universe. Look at this similarity. I really believe that there's a fundamental tie mathematically between these two worlds. Notice here the large-scale structure, you pick a little dot in there, and that's like several galaxies together, right? So this is future research that we'll be exploring. But for now, let us go back to the caustic pattern and look at the issue of extrasolar planets.
The right-hand image,
Yes.
what does the color represent?
So it's a density of the dark matter, right? And the higher densities, so these here, that's like the brightest parts, the most concentration of dark matter. This would be more like the shadowy region. It's more, there's stuff there, but not as dense, okay? So now, what does this have to do with the price of beans? In other words, what is this good for in physics? So let's look at the issue of extrasolar planets. We're all interested in this. Is there life somewhere else in the universe? And is this tool helpful for that? The answer is yes. Remember Einstein's essay? It's remarkable. If you now reinterpret his essay, he said that right here on the line of sight is a very bright spot, that if you sit there, you'll appear as this formally infinitely bright ring. And if you're off it, you'll get double images where one is brighter than the other. If you redo his essay in this framework, you actually discover there's a shadow pattern behind it. And if you are a source and you cut through it, this is how your brightness will behave. It will hit a peak and go down. This thing has a name. It's called a light curve. It just monitors how bright you go. You get brighter, dimmer as you cut through a shadow pattern. Now, what happens if you have a star and a planet? I realize isn't as clear. So here we represented a caustic for you. The first thing is, how many cusps are there? 5. Well, Arlie claimed there's an even number. That theorem isn't wrong. So I just want to remind you, there is another cusp right at that location here. Okay? So let's get back to the story. If you're a source of light and you now cut across this, what happens to your brightness? How does your light curve look? And here it is. I put it on the left for your convenience. So when you're coming along, there you go. Your brightness goes up, down a little. And when you're here, remember there's a lobe in front here. That accounts for this little kink that you see. And then you come and you hit the caustic. And that's when your brightness spikes up. When you're inside, remember I told you it drops down. This is a little U shape. You hit that caustic again, it spikes up, and you go outside into the shadow, and it drops, your brightness drops right down. Okay? So when you have a single star, we know the profile looks like this. When you have a single star and a planet, it looks like this with a spike. That's the prediction. I just put them together to remind you. This is a case Einstein did. That is actual data. This star went through this brightness over like, I think, 20 days or so. And each color, it came from 6 independent telescopes that were observing it. And when you put all the independent data together, you see this. This planet, I think, was like a Jupiter-sized planet. Let me do another example quickly. Here's another shadow pattern. That one is more clear to see. You cut across like this. When you hit that, this is that first spike. When you're inside, you dip down, hit the other caustic, you spike out, and then you go through this. Here's data. Isn't that amazing? It was discovered in 2003. We now have found about 82 planets, and by the way, in the science, you can figure out the mass of the planet, the radius of the light source, and I'm just skipping over all of that. So using the cutting through the shadow pattern by analyzing the light curve, you're able to make predictions like this, and then you go to your telescopes and check to see if it fits.
So is this about a light source behind the star?
That's right. So this was looking towards the center of our galaxy. All these that I'm showing you are planets being discovered looking towards the galactic bulge. All right. Now, this is what I'd like to end with. I think I have about 5-7 minutes. We get a little philosophical here. I'm in this room. I love the geometry of this room. Length, width, height. And then we have time. Arlie has 5-7 minutes left. Is there another dimension beyond length, width, and height? So is there a 5th dimension? if there is a fifth dimension, why should there only be 4 dimensions in total? And why should physical space just be 3? If there is another dimension of physical space, how would we know it's there? Right? That is the big question. And then, can we use this stuff to help with that? And I claim yes. So here's the argument. First, I need to give you cosmology in a minute. I don't know, have you seen this picture before? From NASA, beautiful picture. Here is the Big Bang, the great mystery of how we all of physical reality came about, physical reality we know of. And then there's this rapid expansion. You know, by the way, from here to here, this is today, by the way. You're looking back about 13.7 billion years ago. I like to think about it. My grandmother in Belize had this old-fashioned pressure cooker. And then I'm in the kitchen, a little puppy, yeah? And at the top, it's like, she would say, out the kitchen, and then she lifts the lid, and you step back up. Think of it, that's like what happened here. Except it's physical space expanding out like that. And as this steam goes out, as it gets wider and wider, it gets cooler and cooler, and when it turns to a liquid, that's a phase transition as it gets colder. Then a liquid, when it turns to a solid, that's another phase transition, right? Turns to ice. So you had like 6 phase transitions from here to there. And this is when photons got disconnected from matter, from atoms, and so on. And here's the latest picture from Planck of what the temperature profile of the radiation looked like. The picture I showed you, the large-scale structure of the universe, occurred somewhere in here. All right, so that is it. Okay. We will return to the early universe in a moment. So there is a theory of a 5-dimensional universe called the Randall-Sundrum brain world model. Brain means, it's just short for membrane, and the idea here is that this sheet would represent our physical universe, and in principle, you know, you have length with height. This is a direction of space that there could be another brain. You heard of multiverses, different universes. But let us assume that, for simplicity, this brain is pretty far from ours. We don't want trouble, right? So we'll keep it at a safe distance. And that's called the Randall-Sundrum Model 2. So how would we know that there's a 5th dimension? This is some work that I did with a colleague of mine at Rutgers. And the idea is that we should look for something called a brain world black hole. Now, you may normally think of black holes as these big things that could suck in you and me. That's not what I'm talking about. I am talking about microscopic black holes that were formed in the early universe. Remember that picture I showed you, the temperature profile? That was about 375,000 years after the Big Bang. And you saw the unevenness in it. The blue meant there were more cooler regions. And so the theory tells us that microscopic black holes were formed. In the RS model that it's called, RS2, 5-dimensional black holes should have also been formed. Well, let's take that idea, right? Here's a temperature profile. So let us now, as Einstein contrasted against Newtonian gravity, we need a contrast against Einstein's theory, because Einstein's theory is built on a 4-dimensional universe. In his model, which was that picture I showed you before, the microscopic black holes that would have formed, if they had the mass of an asteroid, they would have fizzled out by now. You have heard of Hawking evaporation? It's because they're pretty hot. And it's so hot it just evaporates out some 13 or so billion years later. Now, the brain world black holes, they have a different temperature law than in Einstein's four-dimensional universe. A temperature law allows them to be cooler. And because they're cooler, they don't fizzle out as fast, and they would persist up to today. And once Chuck and I realize that, we say, aha, we got you. All right, so thinking out loud, right? Let us assume one of these five-dimensional microscopic black holes exists. They're like the size of a nucleus, but the mass of an asteroid. That's kind of a scary fella, right? How would we know it exists? So the way, imagine you have a still pond, and you drop a pebble. You have waves propagating out. Because we are working with such tiny black holes, the action of light is going to involve that kind of rippling, and light will no longer be treated as a ray. It will have to be treated as a wave. So Chuck and I had to develop a wave optics like what Einstein did, but develop a wave optics for lensing by these microscopic black holes. And so returning back to his picture, you're going to actually have what you call a fringe pattern. This is the essence of it. You have bright and dark fringes. This dark part here, say, would correspond to one of the trough, right? It's up and down. So it's one of the valleys in the rippling effect. And remember, this thing is like the size of a nucleus. So it creates a shadow pattern, except it's in this wave optics sense. So we actually worked through all the mathematics of it and came up with a prediction. If you have a brain world black hole and you look at its intensity with respect to energy, you're going to see this wiggle in its energy spectrum. For a five-dimensional brain world black hole. If you have a four-dimensional one, it would be this dashed line. So you could distinguish the observable signature. The energies are not extremely high relative to string theory's energy scale. These are energies for the physicists in the room, about 200 MeVs. That should be accessible to a current satellite up called the glass satellite. If not the glass, the next generation of glass. So you don't need to wait 100 or 1,000 years to have the technology to look for this. And so if we ever see this wiggle, I would say grow an afro, get some bell bottoms and platforms. We will dance to the age of Aquarius, right? To the music of the fifth dimension. Thank you very much.
Okay, so usually we have a microphone available. Maybe I'll go out and get one. But questions? So questions.
There's a microphone.
Let's see if it's live. Yeah, come on. I'm a theoretician. I don't do it. There we go. Okay, questions.
Or comments.
I'll start with one and then two.
Thank you. Are you suggesting that the dark matter is actually gravitation from objects in the fifth dimension, or rather like displaced from in this fifth dimension?
So, there are different models floating around for dark matter. We're still not too sure. The strange thing with the fifth dimension is that there's only one species of physical reality, if I put it like that, that's allowed to transmit between the different brains, and they're gravitons. So it's just gravity that could get from one brain to the other. No one else is allowed. And so that could then be a candidate for dark matter. We're not too sure about its nature. But black holes also would fall in that category. I will say we're not sure at all. Right now, I would think a consensus view would be is that there are certain particles, we're not too sure exactly what they are, that's out there that form this filamentary structure that you're talking about. Now, it's supposed to be in this room, supposed to be passing through you and me. I mean, we're talking about spooks, right?
Right.
But this, again, is, and it's similarly, if the fifth dimension exists, it's to be right here now, just that we can't access it, right? So that is my little thinking out loud response.
Okay, thank you.
Yeah.
Thank you.
Yeah.
I guess I was a little bit enthralled by the caustics, and in particular, I was trying to figure out if there was a criterion for determining the cusp, because you had a case in your history where you found that a missing cusp would actually solve your situation.
Yes.
So how do you verify a cusp?
So I think I know in retrospect, first of all, how Hans found that missing caustic. And it's because that missing caustic, I think, was created by the planet. The planet was 1/millionth the mass of the star, of the parent, and that little baby caustic was sitting on scales close to that, right? So that's like the first hint. Now, if you ask me what is a caustic, the best answer I could so the intuitive answer is it's like what it says. It's a place where a lot of photons, a lot of light pile up, right? And it's where, in principle, infinitely many rays of light pile up there. In a mathematical sense, you can also define what are cusps and what are folds and what are caustics in general. And that involves some very sophisticated machinery that allows you to define it without using any coordinates, meaning independent of observer. So I think the practical astronomer will tell you, I see a cusp. If you see that triplet, remember in the images, say that's a cusp. But it's a little bit of abuse of terminology. Okay. So I should tell you, I only showed you folds and cusps. So the folds are the arc, the cusp are those little pointy things. There's a whole family of higher order singularities. And you have elliptic umbilics, hyperbolic umbilics, every kind of ilic you could think of. But this is a point. Remember, what I showed you are snapshots. The universe isn't static, yeah? Stars, everything is in relative motion. And the caustics engage in a dance, almost like a waltz. You won't believe this. The way, so they merge and then they flow and all this kind of stuff. It's a waltz that has 5 moves. Isn't that remarkable? And this is a mathematical theorem, that you're going to go through 5 different metamorphoses generically that produces this whole complexity of the dance moves. Yeah. Great.
A couple of times you said when there was the ring that was
The
limps,
Einstein ring,
you
yes.
said it was infinitely bright.
So formally, and when I say formally, I meant that if you look at the mathematical equations, they break down there. On the ring, you'll get infinity popping up when you compute the brightness. So in the real world, the source of light is not a point, it has a size. And so that size will then not give you the infinity. So it simply means that the brightness will be pretty high. By that I mean it could be 10 to 100 times what the normal brightness of the star would be. Great. Good.
I have no job.
Okay, I just had a simple question. Why only 5 dimensions? Why not more?
So he asked why 5 and not more. So in string theory, you have much more than 5, but those are in the micro realm, right? They're close to the Planck scale. I hope they are not, you don't have more than 5, because that would be kind of freaky. Right now, the 5 comes about in the RS model because it helps to explain why gravity is weak. So the approach you usually take is Occam's razor, meaning you use the least number of dimensions to get a consistent theory. Right? The simplest structure you could use. Right now we're at 5. Yeah, great. Good. Oh, Tom, yes.
Some people have suggested starting with time, because everything has a time dimension, and then afterwards you count the number of space dimensions.
Yes.
So what you have is 4 dimensions of space and 1 dimension of time, which, by the way, is the same thing that Madeleine L'Engle ended up with when she was doing A Wrinkle in Time.
I
she,
see.
She assumed that there was a 4 dimensions of, three space and 1 time, and you needed another one to do some of the things she wanted to do.
Yes, yes.
But that's awkward to, you have a 5th dimension, but 4 space, 1 time
That's
is
right.
the model.
Yes, that's right. And the thing is, if you allow for 2 time dimensions, all kinds of weird things would happen,
Yes.
including going back in time and killing yourself, right?
For example.
Yeah, right. Good. All right.
More. Some of you look frightened, so why don't you ask?
No.
I'm serious. Some of you.
Well,
I've been teaching. We've both been between us. How long have we been teaching, Arlie?
Oh my
30,
gosh,
60 years?
I won't date myself. So,
So-
but I will just end by saying I know we're a bit over time here, that this is one of the perplexing questions about the nature of physical reality. And the way I think about it is, remember when we thought the world was flat? And then we had this paradigm shifting that the earth is not flat. I believe if we find any supporting evidence for a 5th dimension, it's going to just shift our worldview with that kind of effect, right? So just remember to go out, get the afro, the bell bottoms, and the platform. Thank you.
Thank you, Arlie.
All right.